Today, we're going to study a concept that directly affects aircraft performance and flight safety: density altitude. Every pilot has experienced an airplane that felt strong and responsive on one day and noticeably sluggish on another, even at the same airport. The difference is not random, it is measurable, predictable, and rooted in atmospheric physics. Understanding density altitude is essential because it determines how an aircraft will accelerate, how it will climb, and how much margin you truly have after takeoff. In this lesson, we will do three things. First, we will observe the effect of changing atmospheric conditions on aircraft performance. Second, we will define density altitude and understand what it represents. Third, we will calculate it and connect the numbers to real performance outcomes. The objective is not simply to compute a value. The objective is to understand how atmospheric conditions translate directly into aircraft capability. Let's begin. The first flight demonstrates takeoff and climb performance under standard atmospheric conditions. In this case, field elevation, pressure altitude, and density altitude are equal. These are baseline conditions, the standard atmosphere. Under these conditions, the airplane accelerated to takeoff speed in 33 seconds. From brake release to 1,000 feet above the airport, the total time was 4 minutes and 15 seconds. This result establishes our reference point. In the second flight, we reduced the altimeter setting from 29.92 to 29.42 inches of mercury. This change lowered the atmospheric pressure, increasing the pressure altitude to 8,178 feet. The resulting density altitude was 8,057 feet. Although field elevation remained the same, the airplane was now operating in less dense air. Under these conditions, the aircraft reached takeoff speed in 35 seconds. From brake release to 1,000 feet above field elevation, the total time increased to 5 minutes and 25 seconds. A reduction in pressure alone resulted in a measurable decrease in performance. In the third flight, the outside air temperature increased from negative 0.9 degrees Celsius to 19 degrees Celsius. Although pressure remained unchanged, the higher temperature significantly reduced air density. As a result, density altitude increased to 10,458 feet. The airplane was now operating in air that behaved as though it were above 10,000 feet. Under these conditions, the aircraft required 41 seconds to reach takeoff speed. After liftoff, climb performance was severely degraded. The airplane was unable to reach 1,000 feet above airport elevation. This demonstration isolates the effect of temperature. An increase in temperature alone can raise density altitude dramatically, and with it, reduce aircraft performance to the point where climb capability becomes critically limited. Under these conditions, the aircraft was unable to climb to 1,000 feet above airport elevation. As the airplane continued forward, it crossed terrain that was only a few hundred feet below the flight path. The vertical separation was minimal, well outside the margin typically considered safe for operations in mountainous terrain. In the image, you can see the aircraft passing over rising ground with very little clearance. The airplane is airborne, but the climb gradient is insufficient to outpace the terrain. This is the operational consequence of high density altitude. The aircraft may be flying, but it is no longer climbing with authority. When terrain rises faster than the airplane can climb, performance becomes a safety issue, not just a number in a chart. In this demonstration, the atmospheric conditions remain unchanged. Altimeter setting, outside air temperature, and density altitude are the same as the previous flight. Density altitude remains 10,458 feet. The only variable we changed was aircraft weight, reducing it from 2,556 pounds to 2,021 pounds. With the reduced weight, performance improved immediately. The airplane reached liftoff speed in 30 seconds. From brake release to 1,000 feet above airport elevation, the total time was 2 minutes and 36 seconds. No change in pressure, no change in temperature, no change in density altitude. The improvement resulted solely from reduced weight. All things being equal, reducing weight improves takeoff and climb performance while increasing the maximum density altitude at which the airplane can safely operate. Now that we have seen how density altitude affects airplane performance, we can begin solving a density altitude problem. In this example, the given conditions are field elevation, 5,000 feet, altimeter setting, 30.4 inches of mercury, outside air temperature, 21 degrees Celsius. The FAA defines density altitude as pressure altitude corrected for non-standard temperature. A practical way to think of it is this: field elevation, plus or minus pressure, plus or minus temperature. Step 1, determine pressure altitude. Pressure altitude is field elevation corrected for non-standard pressure. Looking at the correction factor in the margin on the right side of the chart, an altimeter setting of 30.4 gives a correction factor of minus 440 feet. With a field elevation of 5,000 feet, minus a correction factor of 440 feet, the pressure altitude becomes 4,560 feet. Step 2. Locate the outside air temperature of 21 degrees Celsius along the bottom of the chart. From that point, move directly upward until intersecting a pressure altitude of 4,560 feet. This position lies approximately 440 feet below the diagonal line, representing a pressure altitude of 5,000 feet. Step 3. From that intersection point, draw a straight line horizontally to the left margin of the chart and read the density altitude. The density altitude reads just above 6,000 feet. This completes the calculation. In case you were wondering, the departing aircraft in this example is a Boeing 767. Its maximum takeoff weight exceeds 400,000 pounds. Each engine produces approximately 60,000 pounds of thrust, for a combined total of 120,000 pounds of thrust. With that level of power and altitude capability, it may be tempting to assume that density altitude is not a concern. That assumption would be incorrect. Federal regulations require airline operators conducting operations under Part 121 to calculate takeoff performance for every departure, regardless of airport elevation. Performance data shows that when operating from an airport at 8,000 feet above sea level, this airplane's allowable takeoff weight may be reduced by approximately 100,000 pounds compared to its sea level takeoff capability. Even large transport category aircraft are directly affected by atmospheric conditions. Do yourself a favor, always calculate your takeoff performance.